Hello again, everyone. For this video, for the second part of our discussion of the dot product, we're going to be applying the dot product to a real-world situation. We're going to be using the dot product in the definition of work and energy. So sometimes the stuff we learn in class may seem abstract, and you may ask yourself, what use is this to me? But by the end of this video, you will see that everyone on Earth already uses the dot product, and they already are an expert physicist. So we're just giving you the tools to understand the world around you. So the first thing that we're going to need to apply the dot product to a real-world scenario is something called a force. The basic definition of a force is that it's an interaction between two objects that may change those objects' motion. So if we look down here on the lower left, this woman is exerting a force on the wheelbarrow, and as a result, she's changing the motion of that wheelbarrow. This man is exerting a force on this bowstring, and as a result, he's changing the motion of the bowstring. So, how can we use something that we've already learned in class and incorporate that into our discussion of forces? So let's think about the woman and the wheelbarrow a little bit more. What happens if she increases the force that she is exerting on the wheelbarrow? Will the motion of the wheelbarrow change as a result? Yes, it will. The wheelbarrow will accelerate at a faster rate. So a force has magnitude. If she increases the magnitude of the force she is exerting on the wheelbarrow's motion is going to change as a result. What about direction? What happens if she changes the direction of the force that she is exerting? Will the wheelbarrow's motion change as a result? So if you change your force from being straight upwards to being upwards and to the left, is the motion of the wheelbarrow going to change in response to that force? And the answer is yes. So the force has magnitude and it has direction. A force is a vector, and we're going to use force vectors in our discussion of the dot product in the real world. Now that we are familiar with what a force vector is, let's apply this to the concept of work. So work is defined as the energy you may give an object whenever you exert a force on that object. We can also use the dot product to define work. So if we use the dot product to define work, the work is defined as the dot product between the force vector that is exerted on the object and the displacement vector of that object. So work can be defined as the dot product between two vectors. We covered briefly what a displacement vector is in Module B. So if you need a refresher on what displacement vectors are, what they describe, feel free to pause the video and go back to Module B. We are going to go over the diagram that we have here on the lower left in much greater detail. I do want to draw your attention to something special about this diagram. So we have two force vectors on our diagram. They have the subscript of IB. So why is this important? This signifies that this is the force Ian is exerting on the box. And this is going to correspond to a work, the work that Ian does on a box. So let's go ahead and move on to the next slide and do a work dot product example. So in our first example here, we're going to examine the force that Ian exerts on the box in order to determine the work that Ian does on the box. We also have our initial velocity vector for the box here and our final velocity vector for the box here, as well as the displacement vector for the box here. So while the force was being exerted on the box, the box changed position, and that is described by the displacement vector. If we want to find the work that Ian does on the box, we will need to take the dot product between the force that Ian exerts on the box and the displacement vector of the box. So the first step in doing the dot product between two vectors is identifying the smallest angle between those vectors when they're placed tail to tail. The smallest angle between these two vectors when they're placed tail to tail is going to be 0 degrees. So let's plug that into the definition of the dot product. Remember that the work Ian does on the box is equal to the dot product between the force that Ian exerts on the box and the displacement vector of the box. So let's use the dot product definition to simplify the right-hand side. So we have the magnitude of the force vector multiplied by the magnitude of the displacement vector multiplied by cosine of 0 degrees. So what is cosine of 0 degrees going to be? It's going to be equal to positive 1. So let me just sketch in a positive right there. So the work that Ian does on the box is going to be equal to positive 1 multiplied by the magnitude of the force vector multiplied by the magnitude of the displacement vector. So let's have a brief discussion about vector magnitudes really quick. Vector magnitude is synonymous with vector length. So the length of a vector can be positive or 0. We see over here on the left-hand side that both of these vectors have non-zero length. So neither the magnitude of the force vector nor the magnitude of the displacement vector are going to be 0. That must mean they are positive. So the work that Ian has done on the box is going to be equal to a positive number. What does that mean? It means that Ian has done positive work on the box. It also means Ian has given energy to the box. So physically, we see that as an increase in the magnitude of the velocity vector from before Ian applied the force to after Ian applied the force. So Ian has done positive work on the box. Ian has given energy to the box, and we see that as an increase in magnitude for the box's velocity vector. In our second example, let's examine a completely different force to see how much work that force will do on the box. So let's examine the force that the Earth exerts on the box. This is the force of gravity. So the force of gravity is pointing down. Dang it. Force of gravity is pointing downwards. We have the initial velocity vector of the box here, the final velocity vector of the box here. We also have the displacement vector of the box here. The box is still moving in the horizontal dimension, so the displacement vector that we have in this example is the same as the displacement vector from the previous example. We want to figure out how much work the Earth does on the box. So we need to take the dot product between the force that the Earth exerts on the box and the displacement vector of the box. In order to take the dot product, we need to know the smallest angle between the vectors when they're placed tail to tail. So the smallest angle between the force vector and the displacement vector when they're placed tail to tail is going to be 90 degrees. So our angle is equal to 90 degrees. Let's plug that in to the definition of the dot product. The work that the Earth does on the box is going to be equal to the force that the Earth exerts on the box dotted with the displacement vector of the box. We're going to use the definition of the dot product to simplify the right-hand side. So we have the magnitude of the first vector multiplied by the magnitude of the second vector multiplied by cosine of 90 degrees. cosine of the smallest angle between those two vectors when they're placed tail to tail. So what is cosine of 90 degrees? It's going to be equal to 0. Even though, and this is important, even though the magnitude of the force vector and the magnitude of the displacement vector are positive non-zero, the cosine of 90 degrees took the dot product to 0. So the work that the Earth does on the box is equal to 0. So what does this mean physically? In this example, means that the force vector is perpendicular to the displacement vector, for one thing. It means that the force of gravity did no work on the box, so the force of the Earth on the box did no work. It also means that there was no energy given to the box by the Earth. And how do we see this? In our diagram, we see it as the initial velocity vector and the final velocity vector have not changed their magnitude. So the initial velocity vector is equal to the final velocity vector. The force of the Earth on the box has done no work. The Earth has not given the box any energy. Before we move on to our final example, I want to talk about the situation in which we've been calculating work. This box is a box that's sitting on the floor of your new apartment right after you moved in, let's say. And in the first example, we saw how much work the force Ian exerted on the box. We saw how much work that force did whenever it was parallel to the displacement vector. But what happens whenever the force exerted on the box is not directly parallel or directly perpendicular to the displacement vector? What happens to the work in that situation? So in our first example, the force that Ian exerted on the box pointed directly to the right. It was parallel to the displacement vector. In this example, the force that Ian exerts on the box is pointing down and to the right. The displacement vector is still the same. So the displacement vector describes the change in position of the box, and the box is moving in the horizontal direction along the surface of the floor. We want to calculate the dot product between the force vector and the displacement vector. So we need to identify the smallest angle between these two vectors when they're placed tail to tail. So the smallest angle is going to be here. Let's say that that angle is equal to 45 degrees. The definition of work is the work that Ian does on the box in this new example is equal to the dot product between the force that Ian exerts on the box and the displacement vector of the box. Remember, the force that Ian exerts on the box in this example is pointing down and to the right. So whenever we use the definition of the dot product to simplify the right-hand side, we're going to have the magnitude of the force vector multiplied by the magnitude of the displacement vector multiplied by cosine of 45 degrees. So how is the cosine of 45 degrees going to change the output of the dot product? How is it going to change the work that Ian does on the box in this example? Cosine of 45 degrees is going to be equal to positive 0.71. So the force that Ian exerts on the box is still going to do positive work. The box will accelerate across the room, but you haven't maximized your work. You haven't maximized the energy that you've given to the box. It's also worth coming back to the graphical method, the flashlight method that we used in our previous video. So if we grab our flashlight and we shine it directly onto vector F, and we see how much of vector F is parallel to the displacement vector, we're going to get this as our parallel component. And we see that the parallel component has a smaller magnitude than the full force vector. And you intuitively know this. You know that pushing down on the box, like in this example, is going to make it more difficult for you to change the motion of the box. You've already got the physics, you already know the dot product from your everyday life. What we're doing here is giving you the vector math and the vector skills to describe that mathematically. So let's just recap what we've learned today. The general definition of the dot product includes the magnitude of the first vector in the dot product, the magnitude of the second vector in the dot product, as well as the cosine of the smallest angle between the two vectors when they're placed tail to tail. And I just want to reiterate, because that's what this video and discussion is about, I want to reiterate that the real-world application we've discussed today is something that you learned whenever you were a child. By existing in this world and interacting with objects around you, you already intuitively know what a vector is, and you know some of the applications from this class that we're teaching you. You already knew the dot product, you already knew what a force vector is and what a displacement vector is. What we're doing in this class is giving you a mathematical description for those things for the first time.